This lesson looks at using the noble gases as a shortcut for writing electron configurations. It can be used for any element beyond neon, so any element higher than number 10. Let's start by writing the full electron configuration for lead, atomic number 82. So we would need 82 electrons. Following the off-brow principle, we'd have what is written here, 1s2, 2s2, etc., all the way up to 6p2. This certainly gets long and is tedious. So there is a shortcut. How does it work? So you're going to look on your periodic table and go backwards from lead until you come to a noble gas. In this case, it would be xenon, atomic number 54. If I wrote the electron configuration for xenon, it would look like this, starting at 1s2 and going all the way through 5p6. Notice the configuration for xenon, if I'm looking at the highlighted area here, would be all the way up through 5p6. I'm showing it in a different color in our original configuration for lead. So what do? We are going to simply show xenon in square brackets and then write what we have left in the configuration. So we represent xenon by putting square brackets, and I am showing its atomic number there simply to remind you that you already have accounted for 54 electrons. And then we are ending with the 6s2, 4f14, 5d10, 6p2. So in other words, you've started at the xenon point on your periodic table. Again, we can check if we added 54 to 14, 10, and 2 again, it would add up to 82, so we know that we have enough electrons. Summarizing what we did, we can use it for anything beyond neon, and we're going to use the brackets and then continue. So if I had sodium, which has 11 electrons, I'd go backwards on my periodic table. I would be starting with neon, so I would write neon in square brackets. That is representing 10 electrons, so in the full one, everything up through the 2p6, and I simply add 3s1 at the end. Another example with the shortcut. Iodine, atomic number 53. So if I find iodine on the periodic table and move backwards till I hit a noble gas, I would see that I would start with krypton. It's atomic number 36, and then I'm going to continue from there. So I would have krypton in square brackets with the 36, and then I am going to continue. I'd add 5s2, 4d10, 5p5. I'm ending right where iodine is on the periodic table. If I add these numbers up, 36 plus 2 plus 10 plus 5, I get my 53. I know that I have accounted for all the electrons. If I want to do the electron orbital diagram, I'm going to do the same thing where I would start with krypton, and then I'm only going to draw the orbitals for what we show here after the square brackets, the 5s2, 4d10, 5p5. So we'd have krypton, and then we would have our remaining orbitals. So 1 for the S shape, identifying those. We draw 5 for the Ds, all up and down. And following Hund's rule, where we have 5 electrons to go into the p orbitals, we would fill in 1, 2, 3, and then 4, 5. And I realize on these arrows I put the downs first instead of the ups. Please forgive me. We can also use the electron configurations to illustrate ions. And this is very powerful. This is where we start to see the similarities of different elements on the periodic tables and their properties. So let's look at the cations first. So cations lose electrons. So we'll use aluminum, which would have a 3+ charge as our example. And that would have a total of 10 electrons, because aluminum as a pure element would have 13, atomic number 13. 3+ is reminding us that we have lost 3 electrons. So our electron configuration only needs to show 10 electrons. So we will go 1s2, 2s2, 2p6. Let's look at another example. Calcium. Calcium ion, calcium 2+, would have 18 electrons. Calcium as an element has 20. I've lost 2, so the calcium ion has 18 electrons. The electron configuration starting at 1s2 will be 1s2, 2s2, 2p6, 3s2, 3p6, adding up to the 18. Notice that our final configuration for aluminum with 10 electrons looks identical to what we would write for neon. For calcium with 18 looks exactly what we would write for argon. So both of these ions resemble a noble gas. This is why the ions are so common and stable for these particular cations. All right, how about our anions? Anions gain electrons. Let's use the nitride ion as an example. That would be N3-. The ion would have 10 electrons. Nitrogen as an element is atomic number 7. -3 means I've gained 3 electrons, so I'm adding 3. So I have a total of 10 electrons I must show in my configuration. 1s2, 2s2, 2p6. That 2 looks exactly like neon, as well as the aluminum ion. Another example, sulfide has 18 electrons. Sulfur by itself is 16, 2-, I gain 2. I also have 18 electrons. My electron configuration looks exactly like argon and also exactly like the calcium ion. So our anions also end up resembling a noble gas when they are written as their ion, and that is why they like to gain the particular number of electrons they do, so that they are stable with a noble gas configuration. We have a very special vocab word for elements that when we write their electron configuration, they are identical, and that word is isoelectronic. Iso meaning same, the same electron configuration. So we would say that the aluminum ion is isoelectronic with neon. The calcium ion is isoelectronic with argon. In looking at electron configurations and the periodic table, it's important to distinguish between what we call the valence electrons and the core electrons. Valence electrons are the electrons in the outermost shell when we are writing the configurations. So those would be the electrons that would have the highest n value, the highest coefficient when we are writing them. These electrons are the most important because the valence electrons are those that are involved in chemical bonding. That's why we care about those a little more. If you are not a valence electron, so anything that is not a valence electron is inside that outer shell, and it's referred to as a core electron. Let's use silicon as an example to illustrate valence and core electrons. To start, we would write the electron configuration for silicon. So 1s2, 2s2, 2p6, 3s2, 3p2. Valence electrons are those that have the highest energy level. So I look at all my coefficients and I see the highest coefficient is 3. So I have 3s2 along with 3p2. So all of these shown here in yellow are valence electrons. So I would have a total of 4, 2 plus 2, 4 valence electrons. Anything that isn't on that is considered a core electron, and we have 6 plus 2 plus 2, 10 core electrons for the total of 14 that we have for silicon. Let's look at an example where we have some d orbitals involved because we have to tune in a little more. We're going to use selenium. Selenium is atomic number 34. So if I write our configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4, I want to separate my valence versus my core electrons. So the valence electrons will be those with the highest coefficient. So I look and that is a 4. Now be careful. We have the 4s2 separated by the 4p4 because the 3d10 are filling in there afterwards. But the 4s2 and the 4p4 are both groups of valence electrons because they are on the outermost shell. So I have a grand total of 2 plus 4, 6 valence electrons. All the others shown in blue are core electrons. I add those together and I have 28. Notice 28 plus 6 is going to be a total of 34. So any electrons, including those in the 3D, are all core electrons. So the quantum mechanical model, which focuses on looking at our electrons in terms of where they're most likely to fall and separating our core versus valence electrons, helps us to see that the chemical properties of elements are very much determined by the valence electrons they contain. So these properties vary in a periodic fashion because of the number of valence electrons on the periodic table. I do want to comment that when you look at a table of electron configurations for all the elements, particularly when you hit some of the transition metals and our lanthanide and actinide series, you are going to come across some exceptions to the electron configuration pattern. All of those exceptions occur, they break the pattern because they will be more stable, and that is why that occurs.